Hi, I'm Cassie, and I'm going to walk you through question 53 of the AAMC's official physics question pack to help you prepare for the MCAT. So this question is all about understanding two really important concepts for the MCAT. The first is going to be how capacitors work, and the second is going to be how resistors work, both variable and fixed resistors, and specifically what effect that they're going to have on our capacitors. So let's get right to it and look at our answer choices. So the correct answer choice here is going to be answer choice C for me, which says that charges can't accumulate indefinitely because successive charges brought to the plate are repelled by charges accumulated earlier. So to understand why this is the case, you need to understand how a capacitor charges. So let's draw a super simple circuit here with the capacitor. So all I'm going to have in my circuit is my capacitor. Remember, that's just two metal plates with a gap between them. So that's two conducting plates. And we've got our capacitor is going to be connected some sort of source of voltage, usually a battery. So we're going to have our negative plate of our battery being our shorter line and our positive plate of our battery being our longer line. And remember that what capacitors do is that they store charge. Remember, our equation for capacitance is just going to be capacitance is equal to charge, or Q, stored at a certain voltage. So that voltage, of course, that is going to be stored in the capacitor is going to come from our battery. So how does this process of charging the capacitor work? Well, we know that we have our positive terminal of our battery here, and flowing charge is just electrons or negatively charged particles. So those negatively charged particles are going to be attracted to that positive terminal of the battery. So what's going to happen essentially is going to have my negative electrons, and they're going to be continually being pulled towards that positive charge of the battery. And what's going to be the result of that? Well, if our negative charges are going away from this right capacitor plate here, ultimately we're going to get positive charges building up on our right capacitor plate. And now at the same time this is happening on the other side, on our left capacitor plate, those negative charges are getting repelled from the negative terminal of the battery. And so the result of that is we're ultimately going to get, for every one positive charge that builds up on our right capacitor plate, we're going to get one negative charge building up on our left capacitor plate, because our two capacitor plates are going to have to store equal and opposite amount of charges. So in other words, if this left plate had a charge of -3 coulombs, this right plate would have to have an equal and opposite charge of +3 coulombs. But this process can't just continue forever. Our capacitor is going to have a max amount that it's able to charge, and that max amount is going to be equal to whatever the voltage of our battery is. So we said that our negatively charged electrons, they're going to be getting repulsed from this negative side, this negative terminal of our battery. But eventually we know that negative things, they repulse other negative things, right? So this negatively charged particle might be trying to come and join its friends on the left plate of our capacitor here, but they're going to eventually start pushing back really strongly. And so that negatively charged particle here, it's not going to be able to accumulate with its friends on that left plate of the capacitor. Likewise, on the right side of our circuit here, right, we said our negatively charged particles, they were getting drawn to the positive terminal of our battery. But eventually, they're also going to be getting drawn to the positive charge that accumulates here on the right side of our capacitor. They're going to reach a point where there's equal force essentially pulling on each side, pulling them towards that positive terminal of the battery and towards the positive plate of the capacitor. And so again, we reach a sort of equilibrium where the capacitor is not going to accumulate any more positive charges on this right capacitor plate, and that's when we know our capacitor is fully charged. And then what happens? Well, the capacitor is just going to keep this charge sitting here stored for whenever it needs to be used. Like, for example, when you have a defibrillator, you have the two capacitor plates that you put them on the chest of someone who's in cardiac arrest, and then all of a sudden the stored charge from those two defibrillator plates, they go through the person's body and can essentially shock them back to life. So that's the idea of a capacitor. So again, that's why our answer here is going to be that more charge can accumulate because it's going to get repelled by the charges that already accumulated on our capacitor plate. Okay, so now let's look at why the other answers are wrong, and that's going to really help us understand what resistors are and how they work. So answer choice A for me is wrong, and it says that the variable resistor inhibits the current flow, and that's why more charge can accumulate on our capacitor plates. So let's take a look at our circuit diagram that we have here. So what are all of our circuit components here? Well, we have our battery, it's providing the voltage to our circuit. We have our fixed resistor, our little r here. We have our capacitor over here. We have a switch that can be switched on or off to complete the circuit or to leave the circuit incomplete. And we have our variable resistor over here. And then this A here, remember, is just an amp meter. The current flows through it and measures how much current is in our circuit. So this answer choice focuses on our variable resistor here. And remember, a variable resistor is just a resistor where you can turn up or turn down the amount of resistance. So you can put the resistance at a certain setting depending on what you want. And it's saying that charge won't accumulate because our variable resistor is inhibiting our current current flow. But is our variable resistor even going to be involved in the process of charging our capacitor? In this case, the answer is no. Why? Well, the question tells us specifically that our switch here, our S, is closed, right? We can assume our switch is closed. So our circuit is closed here. So when we go to charge our capacitor, just like we drew out earlier, those positive charges are going to build up on one plate of our capacitor, and the negative charges are going to build up on the other plate of our capacitor. And so that process, where is that happening? That process is happening here. It has nothing to do with what's going on with our variable resistor over here. So our variable resistor is irrelevant to our process of charging here. And they even tell us this in the passage, right? They tell us in the passage that our variable resistor is only at play when our capacitor is discharging or releasing the charge is already stored. The kind of resistor that the passage tells us is at play, and we can see here in our diagram when our capacitor is charging, is going to be our fixed resistor right here. So that's why this answer choice is wrong. Now, the answer choice could have been worded differently here. Could have said the fixed resistor inhibits the current flow. That answer would still be wrong. Why? Well, then we'd be talking about this resistor. And it is true, our current is going to have to flow through this resistor when our capacitor is charging, because this fixed resistor is in series with our capacitor here. But how does a resistor affect the charging or the discharging of a capacitor? Having a resistor in our circuit is going to affect our rate of charging or our rate of discharging. So that's the role of resistors. They allow us to control how fast we charge or how fast we discharge a capacitor. And why is that? Well, remember that our equation for Ohm's law is V equals IR. And therefore, if we solve it for current, we get current equals voltage divided by resistance. So when we add a resistor, if we increase our resistance, we know we're going to decrease our current because they have an inverse relationship according to our equation here. So all that tells us is that when we add in our fixed resistor here, our current that's flowing through our circuit pushed by the voltage from our battery is going to be less. And because our current is less, our capacitor is going to charge at a slower rate. But ultimately, the resistance does not affect the max potential, the max capacity that our capacitor can charge. Why is that? Well, we said that our equation for capacitance is just going to be charge, Q, stored at a certain voltage. And therefore, if we solve that equation for Q, charge, the max charge that a capacitor can hold, we're going to get our Q max is going to be equal to our capacitance, our max capacitance, times the voltage coming from our battery. So notice that resistance is nowhere in that equation. So how much resistance we have in our circuit, it's not going to affect the potential amount that you could charge your capacitor, the maximum amount of charge that the capacitor can hold. The only two variables that affect the maximum amount of capacitance that that capacitor can hold are going to be our capacitance and our voltage. And we know our voltage is just going to be coming from the battery. And in an earlier question, we talked about how our equation for the capacitance of a capacitor is going to be AKED, right? Where our capacitance is equal to the area of overlap between our capacitor plates, K, which is if we add a dielectric material, some sort of material between our capacitor plates, it's going to increase our capacitance, E, which is just a constant called the permittivity of free space, and then our capacitance is inversely proportional to the distance between our capacitor plates, or our D here. So to sum it up here, our resistors are going to control our rate or our speed of charging or discharging our capacitors. They are not going to control the max amount of charge that our capacitors can hold. That just depends on their capacitance and the voltage from the battery. So we know that whether we're talking about a variable resistor or a fixed resistor, it's not going to control how much charge can accumulate on our capacitor plates. So that's why this answer choice is wrong. So another incorrect answer choice here was that the battery continually loses charge, and that's why charge can't accumulate indefinitely on our capacitor. Batteries are meant to provide a stable, constant amount of voltage until all of their, chemical reactions are depleted. And that process of depleting the chemical reactions of a battery takes a very long time, right? Usually hundreds or even thousands, depending on the type of battery, of hours. So yes, batteries can lose charge, but batteries losing charge is a process that's completely separate from how much charge you can put onto a capacitor plate. Remember, we just said in the last question that how much charge you can put on a capacitor plate is going to be given by the equation. Our max amount of charge is equal to the capacitance of our capacitor, the max amount of capacitance of our capacitor, times the voltage from our battery. And that this max amount of capacitance can be broken down in the equation C equals AKE over D. So it is true that the max amount of capacitance depends on the voltage from the battery, but this voltage is just a stable number. Like let's say this is, 20 volts. In the time it takes to charge our capacitor here, that 20 volts is not going to get depleted, right? We're not going to just run out of our chemical reactions in our battery in that time. So that's why this answer choice is wrong too. So our last wrong answer choice here says that the fixed resistance resistor loses energy to heat, and that's why charge can accumulate indefinitely on our capacitor plates. Well, that's going to be wrong because here's our fixed resistor, right? So we can just zoom in on the part of our circuit here that's relevant to charging our capacitor. So it is true that the resistor is going to turn some electrical energy into heat, but this doesn't stop the capacitor from charging up as much as it possibly can. The resistor's main job, as we said here, is to control the rate at which the capacitor is charging or discharging. And the loss of heat here is going to affect how much total energy is used in the process, but it's not going to affect how much charge the capacitor can ultimately store. The amount of energy that's used in the process doesn't determine our max amount of capacitance here. So what are our key takeaways from this problem? Well, first, you should definitely have that equation for general capacitance in your equation deck, which is just going to be capacitance equals charge stored at a certain voltage. And that makes sense because that's just what capacitance is. Capacitance is stored charge. That's what capacitors do. They store charge. And you should also take away from this problem the concept of how capacitors charge. And when capacitors charge, we said that we get negative charges building up on one plate and we get positive charges building up on the other plate. And we reach a sort of equilibrium point where if you try to push any more charges onto either plate, like if I try to push a negative charge onto this plate here, well, it's going to be repulsed by these negative charges. And over here, if I try to push a negative charge, and over here my negative charge is going to be equally drawn by the positive charges built up on my capacitor plate and the positive charge of my battery. So on both sides, I reach a point where I can't push any more charges onto my capacitor plates, and at that point, my capacitor is fully charged. My other takeaway here is what happens if I add a resistor into this circuit? So let's say I add a resistor here. What effect is that going to have on my capacitance or how my capacitor charges or discharges? Well, all it's going to control is going to be the rate at which my capacitor charges. It's not going to affect the max amount that my capacitor can charge, and we know that because if we solve our capacitance equation for charge, we're going to get that our max charge is equal to our capacitance times our voltage. And notice that resistance is nowhere in this equation. So the amount of resistance in our circuit is irrelevant to the theoretical maximum amount of charge that we can charge our capacitor. And using variable resistors is really cool for controlling the rate at which a capacitor discharges, because that can be important for a ton of stuff in science, right? Think about a defibrillator. If you're going to suddenly unleash a lot of stored charge from a capacitor into someone's chest, you want to unleash the right amount of charge. And by setting that variable resistor to a certain setting, you can control the rate at which the current flows in your circuit, and therefore you can control the rate at which you discharge, you release that charge from your capacitor. So I hope this helps. If this helps, please give this video a like and follow my channel for more content like this.